So, good day to everyone. My name is Taras Savchenko, and I will be the speaker on the topic Information Extremal Algorithm of Machine Learning for Increasing the Relevance of Classification. A large number of sectors of human activity require up-to-date geographic information about the area. Nevertheless, unmanned aerial vehicles equipped with onboard recognition systems are typically used to obtain it. Such a tool can be useful for escorting a vehicle, assessing soil conditions, analyzing infrastructure networks, for example, detecting damage to roads, railway tracks, water supply systems, and so on. Special attention in the military sector. Well-known methods of intellectual data analysis, including artificial neural networks, have a number of drawbacks that become apparent when processing large volumes of data under arbitrary conditions for generating images of the terrain. Therefore, creating a machine learning method that is flexible for retraining by expanding the recognition class alphabet is a relevant task. The main goal is to enhance the functional efficiency of the onboard system of the unmanned aerial complex for autonomous object recognition. The formalized formulation of the problem of information synthesis for the onboard recognition system involves searching for the maximum of the averaged information criterion for optimizing machine learning parameters based on the alphabet of classes. This slide shows the information criterion applied in the work for optimizing machine learning parameters based on the modified Kullback measure. An iterative machine learning algorithm for optimizing the system of control tolerances based on recognition features. At the same time, the delta parameter is optimized, which, as shown, equals half of the symmetric tolerance field. Thus, the idea of the algorithm lies in searching during the process of information extreme machine learning for the global maximum of the information optimization criterion that was demonstrated earlier. This slide shows the classifier built using the optimal geometric parameters obtained during the machine learning process, according to which the feature vector in the exam is assigned to the recognition class that has the maximum positive membership function mu. So, since the classifier are built within the framework of geometric approach, they, unlike artificial neural networks, are characterized by high recognition speed, which is extremely important as identification on board the drone will occur in real time. To form the input mathematical description, a tree model of the terrain was used, which allows not only to verify the accuracy of recognition but also to conduct a series of interactive experiments to confirm or refute one's own hypothesis. The slide shows the input image and the alphabet of classes, among which we are most interested in objects of anthropogenic origin. The optimal value of the field parameter for control allowances is difficult to determine visually using a graph, as the criterion reaches its maximum value not a single point, but forms what is known as a plateau. Since we are binarizing the map, we need classes that will cover the maximum possible number of features. So, To choose the best delta value, we will apply the distance criterion. Thus, the distance between the classes should be maximized. In our case, this is possible with the parameter set to 33. Since the criterion has already reached its maximum limit, there is no point in sequentially optimizing the control tolerances. Next, on this slide, you can see the graphs showing the dependence of the normalized information criterion on the radii of the recognition class containers based on which the classifier was built. The visual analysis shows a high reliability of the classifier. Nevertheless, it cannot be claimed that when external factors intervene, the objects will be recognized as well. Let's conduct an experiment where, under initial unchanging conditions, we add a barely noticeable haze that will cover the receptor field of the drone. Let's try to identify a new informational description of the area. So, it is not difficult to notice that the system mistakenly identifies noisy frames as technological objects. To overcome this problem, it is suggested to use a priori statistical information about each recognition class. We are interested in the average brightness, average variance, and standard deviation for each of these metrics. The idea is to identify some common indicators that characterize each of the classes. The input sample used the identification result, which is considered reliable. Thus, it was found that all frames classified as technogenic objects have an average brightness value of 73 with a standard deviation of 15. Upon receiving this statistical information, we create an additional quantifier to verify classification decisions, which will be applied during the examination stage. Upon re-identification of the noisy image, a significantly better result can be observed. In most cases, the system ignored the frames with haze, classifying them as undefined zero class. Regarding the viability of such an approach for a more accurate result, it is necessary firstly to have a larger sample size, and secondly, it is advisable to use significantly more advanced metrics than just the average brightness value of the frame. Two significantly new approaches were used during the work. The first is the application of an artificially created information description of the area with the verification of the functional effectiveness of the onboard system within the framework of a computer simulation, which not only allowed for the assessment of the reliability of object recognition, but also enabled the experiment to test one's own hypothesis. The second innovation is the development of a model that ensures the relevance of classification decisions at the examination stage by obtaining prior statistical information about the research object. Thank you for your attention.